Our next speaker, Pedro Porto, and senior research associate from University of Cambridge.
Yes, and Pedro is going to talk in a about a very interesting subject. And actually, I was in charge of reviewing the project, and I found it very interesting. It's about the subject of learning models. So when we have a robot that has to learn several models of the world in order to understand it or to do the task that it has to perform. But what happens if you have so many models? So this single robot cannot learn everything by itself. It will take forever. So then here it comes a concept that is the one that Pedro is going to talk about, federated learning, which is when you have many robots. Each robot is learning its own models, and then it can share with the other robots. So all the robots know about all the models of the other robots.
Wow, that's amazing.
Yes, and that's the speech of Pedro that he's going to talk here. Let's see if Pedro is ready. Hello, Pedro. How are you doing?
Hello, Ricardo. I'm doing well. How are you?
Fine. I'm eager here to listen to the final presentation of your ROSDevDay. And if you are ready, then the audience is yours.
Great. I'm ready. And well, you basically gave a very good definition right in the beginning, but I'll try to give another one for federated learning. So welcome everyone to this ROS and Flower ROS meets Real Federated Learning ROSDevDay. So my goal for you today is to briefly introduce what federated learning is, and then describe this Flower project, which is, well, full disclosure, is the project for federated learning that I work on. And we will go through this definition of federated learning, presenting Flower, the federated learning framework, through an example. One example that is kind of like the one that some of you might have seen with the live class 119, if I'm not mistaken, which uses YOLO. But before we go there, can everyone see my screen? I think so. So first question is, what is federated learning? The best way to explain what federated learning is by looking into centralized learning, the regular learning that you see when you train a neural network. So how does it work? What happens when you train a neural network? So usually you have a model, you have your data set. Most of the times your data set will not fit on your GPU. You usually use GPUs for training. So you divide your data set into mini batches. You perform the regular training, as in you perform the forward pass, you get some errors, the loss, and you calculate the gradients with respect to that loss. So for example, the example of object detection, which is the example that we'll be seeing in this ROSDevDay, you have images that you want to detect bounding boxes over them, and the network will tell you the position of the bounding boxes and the class of the object that it detected. Now, when you perform regular centralized learning, you calculate the error of those bounding boxes, the position, how big they were, if the class that the object that was detected was correct or not. These are all losses that we'll see later. You calculate the gradient, and then you change the parameters, you change the weights of your model. So basically, deep learning in general relies on this gradient-based learning. So you calculate gradients with respect to some loss, and you apply those gradients to have a better model that behaves better on your data. Now, when you train a neural network on your computer, you do exactly that. When you have a lot of data and your model is larger, then you need more GPUs. If you have even more data and your model is even more complex, what you have is nodes. You start working with a distributed system. So for example, what Google does, what Amazon does, they have a lot of data, they have different nodes. Each node will have separate data. And you will do basically what you would do in your regular GPU. You would train each one of the nodes. We'll train on their data. We'll calculate gradients. We'll send the gradients for each mini batch to a server that will aggregate those gradients, apply the gradients to your model. You have another model, and then you send back the models to all the nodes that you had. Now, there's one small problem with that. It doesn't scale very well. So when you perform training on your regular GPU on your computer, things go fast. If you cannot train on your single GPU, you buy a new GPU, and now you start having bottlenecks because you have to communicate between different GPUs. And as you go along, and you start using nodes, each node separate, and you have to communicate those nodes, those computers between themselves and the server, then you start using optical fiber. And although these are very fast, you still have a lot of overhead in communication, in getting back those gradients after each mini batch. So what people came up with, they asked, well, okay, so after each round, after each training, after each mini batch, I have to collect those gradients back, and that takes a long time. What if instead of doing that, I don't have? What if I don't? I just leave the nodes be, and the nodes will perform local training, update their own models, and then after a while, I aggregate those models after maybe 30 epochs or 60 epochs. I aggregate those models, and then I try to come up with a model based on these models. Okay, so a key difference is in regular training, regular distributed training, I would have each one of those nodes always working on the same model at every single time and communicating a lot of gradients. And basically, gradients are as big as a model itself. So what happens is you avoid having this kind of communication, and you let them train. You get back the models, and you try to aggregate. This is a keyword. Aggregate those models into a better model. And this is basically what you see in this image here that describes the federated learning. So you have a model in the cloud. You send this model to the cloud to be shared among different devices. They will perform training on their local data. And these changes will be then aggregated into the cloud. One side effect, one benefit of that is that if you're doing the training on a local node, you can also optimize, not only contribute to having a general model, but you can also fine-tune that contributed model to your data set. Okay, so briefly, this was the idea, the original idea of federated learning, to together train a single model. But you do have different types of federated learning scenarios. So they usually come into two different flavors. One is when you have a lot of data distributed. For example, when you have multiple cell phone devices that and you want to train a model, we'll see an example for learning a language model based on text for each one of those devices. So you have a lot of millions of devices. You never know when those devices will be connected or not. Sometimes you can lose connections. Sometimes you don't want to have your device doing some kind of training locally when you connect it to a paid 3G, 4G, but only when you're connected to Wi-Fi and plugged into the power socket. And this is what it's called the cross-device scenario. Another scenario for federated learning is when you have devices, let's call them like this, devices or clients with more availability. And one typical scenario of that, typical scenario where you have a lot of availability is this cross silo. So for example, you have hospitals that want to train a cancer segmentation model based on their own data set. Of course, they want to collaborate You would like to have one a model that's really powerful, but sometimes you do not have yourself enough data. What you do, you try to collaborate. But as we'll see, in the case of medical imaging, you do not have the right to simply share data. So this is actually one other use case for federated learning in this cross-device scenario. But again, they all rely more or less on the same structure, that they will have their data, you will send a model to them, they will train locally on their data, they will then send their models back to you as a server. You as a server, you will aggregate those weights, maybe using a algorithm that is as simple as the regular FedAvg, which is the federated average, where you basically get the average of each weight from the models that you gathered. Or you can go as complex and try to have not the, let's say, the best overall model that will give you one accuracy, but you can try to maintain a kind of equal accuracy across all the devices. And that's where you start looking into maybe more complex aggregation strategies, such as the QFed average. Okay, so now that we have this system where we can train in different nodes, in different devices, without having to send data, what are the use cases for this? So basically, why federated learning, right? So there are a few cases where you really, really don't want, or you cannot share your training data. And here I put a few of these cases. So if you think about your text messages, we recently had WhatsApp changing their terms and agreements. I didn't quite understand what it is going to be. It is going to do with my text, but if I learned correctly, apparently my text will be shared with some companies. I don't know. I didn't quite understand, but still, I don't want my messages being shared with other companies. So one way that federated learning can help us is that when you're trying to text, when you're typing down a message and you have that model, that next word prediction model, this is based on a neural network. And the neural network usually trains on your data, on your device. Google is actually working on this. If you Google about federated learning, you will see that one of the papers on federated learning is about this language model, that an experiment that Google ran, where each device would learn on their own data, on their own text, and in the end, you would have one model that was able to predict the regular texting property that we have when we're typing and what's the next word and next word prediction. So Google has a paper on that, and Google also has a kind of federated learning framework, but it is using it only for simulations now. If you Google TensorFlow federated, you will see even a demo on how to train neural networks for next word prediction using the, again, simulated framework. So this is one thing that we can use federated learning. Another one is maybe like we saw in the previous image. I want to train a model that is good for everybody, but I also want to fine tune all my data without having to send my data to a company, to a centralized server that I have no idea what they're going to do to it. Okay. One example is personalization of speech recognition. Now, if you have a Google Home device and someone in your house asks, hey, Google, find my device, probably Google will say, I do not. Yeah, there you go. Probably Google will, if it identifies your voice, it will find your device and it will start ringing. If it's a different person, well, then probably you will say, no, I cannot identify your voice. I'm not going to make your cell phone ring. So this kind of personalization is being fine-tuned to your voice, and you probably don't want to have any kind of fingerprint of your voice going around the internet. As I previously mentioned, the cross-silo scenarios. One scenario is when you have data that you really cannot share, like private data, like medical data, but yet you want to develop a model that will be good for everyone. And in the example that I gave for cancer segmentation, this is one of the classic ones. Actually, NVIDIA has a kind of federated learning platform for medical applications called Clara, that you guys are welcome to look it up as well. And it performs exactly this operation of image segmentation. And that you can connect various hospitals to train one single model. And when we start talking about robotics, which is the ultimate goal of this conference, there are quite a few scenarios where federated learning will shine very soon. So one of them is for sure navigation. So we know that neural networks, when we train neural networks, we have to pay attention not to train it on the very same data all the time. So imagine that we want to train a neural network to do navigation inside this house where I am right now. If I only give it data about this house, it will perform well, it will be trained correctly. But then if I just give my robot to my neighbor, then it would probably have overfitted the model to my house and will probably not be able to navigate properly. So this example is actually something similar that we're going to do today on the demo. We will have multiple robots, each one having different data, and they will train in a federated way so that they will generate one model that will help them in their own tasks. So when we go to federated learning in robotics, like I said, there are a few cases where you can apply federated learning. The most obvious one is the self-driving cars. First of all, because when you're using self-driving cars, you basically use cameras, right? You have to detect pedestrians, you have to detect traffic signs, you have to detect the lane if you're still driving at the same place. So when you use cameras, you actually generate loads and loads of data. You might not want to, first of all, send all that data to a server for training. It might not be feasible. Another thing is maybe you don't want the company Tesla to know where you've been driving through. It's a matter of privacy at the end of the day. So self-driving cars, having your car, once you park it in your garage and you connect it to the power supply, and you have maybe an NVIDIA Xavier or some embedded form of GPU, you might as well just train it locally and then again send the weights to Tesla that will aggregate and get a better model, give you back a better model of a self-driving car. Another application could be object manipulation, where you have multiple robots having robotic arms that have to manipulate objects in some way, and they're being used with different objects. So you can kind of parallelize this kind of learning and again generate a better model for everyone. Finally, one other example, which is the main toy example that we'll be using in this ROSDevDay, is when you want to collaborate. You have to create some kind of collaboration between companies that develop robots. So in our case, in our toy example, we have two robots. Each one of these robots were trained on their local data, and their ultimate task is to identify objects that are in front of them. The ultimate task is to do object detection on what they're seeing. In our demo, we're going to use YOLO version 5 as the model, as the neural network. And we will consider two classes, one class of elephants and one class of person, because who doesn't want to detect elephants and people in an image, right? So the way this demo will be carried out is we will first show what happens when you have a robot looking at a person and an elephant. If this robot was trained only on data that contain humans, and what happens when you show the same scene, more or less, to another robot that was only trained on data that contain elephants. We will then show how we can change our regular training code that was developed to be used in a centralized manner, how we can change it using Flower to a federated setup. Then we will see how we can create the ROS nodes using Flower for federated learning. And finally, we will launch the training, and although we won't have enough time to really perform the training, we will launch the training, then we will stop the training and load the final model that I have trained previously, and see the final effect of that, of having one model that was trained using federated learning, where each one of the robots use their own data. Okay, so let's start by looking at our world, our simulation world. So in our example, like I said, we have two robots, in this case, two turtlebots. Now we know that turtlebots, they come with cameras. Oh, sorry. They come with cameras. These are turtlebot 2. And they come with Kinect RGB cameras. So first of all, let's see what these robots are doing, how they're positioned. So what we do here first is we launch a Gazebo simulation where we will find those two robots, a few people in the scene, and one big elephant in the room, because why not? So now we launch the Gazebo. And here is what we define as our world simulation. Okay, so you can see the two robots here, and you can see the world here. Two people. So usually when I launch this this Gazebo, this person here starts to shake a bit, and I'm always a bit worried that it will fall. It will fall, but never happens. Okay, so this is our world with elephant, people, and now we want to see what the robots are seeing. And to do that, we have to open RQT and connect to those topics. Start listening to the topics that give the compressed version of the RGB images for each one of them. So we come here, we call RQT. Open the graphical tool. And Ricardo was nice enough to provide me with a set of perspectives that you will also have with you, which is called this RQT for cameras perspectives. which basically will give us space to load different cameras. So first we load RGB compressed. Let's verify that we're seeing all the cameras, yeah. Actually don't follow why I'm not seeing the Ricardo, am I doing anything wrong? Okay, let me try to quit this and try to reopen it.
Hey, Pedro, can you check
Yes.
if the simulation is running properly? Where did you launch the simulation?
So I launched the simulation right here.
Okay. No, it's yeah, but in which terminal? Ah, there, this one.
Yeah.
Exactly. And can you open the Gazebo window?
Yes.
The Gazebo window, which is on the icons down. Yeah, that one.
That's the one.
Open. Yeah. Okay, so we have the robots there, right?
Yep.
Perfect. Then the problem is with the cameras. And then let's have a look if the cameras are being shown. Then as a topic first.
Yes.
Let's go to the ROS topic list. Yeah, you have to.
So this is the one, right?
Yes, here. That's yeah. So is the topic of the cameras?
Yep. There should be these ones.
Yes. Okay. Great. Then let's launch again the RQT and load the. Yeah, it looks. Oh, okay. That's a good test also.
So
The hertz to see if it's publishing also. Yes. Sorry, I have some delay in the image here. Let me. Yeah, now I don't have the delay. I'm watching on another computer. Yeah. Okay.
This is odd.
Yes. Okay. So it's not publishing then. First, the best option here is to close the simulation and start again.
Okay. So
Thing. On the simulation, yeah, you can close everything. Go to the terminal where you launch it. And yeah, Control C everything and let's start again. There should be a problem here. Yeah, let's have a look when it launches the simulation if there is any error that appears there. Then the audience, if it's there, if they have followed the instructions of Pedro and you are getting the images, you can tell us. Okay, looks like it's correct. I think
Oh,
it
there
is.
we go.
Yeah.
Perfect.
Yeah.
Thank you, Ricardo.
Okay.
Yeah. So yeah, a little bit of Control C, Control Z, or Control D sometimes helps. So let's just make sure that we're using the compressed version, just so that we save some bandwidth. So now you can see the view of each one of those robots, right? So you have the robot 1, and it can basically see partially the elephant and the entire person. The robot number 2 can only see the person. Okay, so this is the view, but now let's see what they're actually detecting. And to do this, I created a YOLO object detector for ROS that you're welcome to inspect. Let's say over here. And what it does, it's a basic ROS node that will apply YOLO to each one of the frames that it receives on that specific topic on the compressed version of the RGB for each one of the robots. It will apply the detection using a given network, a given set of weights. It will create the bounding box around each one of those objects using this bounding box. And it will then publish the new image with the bounding box into a different topic. Now, since we have to use 2 of these, I ended up creating a launch file, which is our this launch detector's launch file. And you can basically see that since we have 2 robots, it is good practice to create different namespaces for those. So here we actually create just 2 nodes. If you go inside each one of the robot definition, you will see that cameras have their own namespaces and so on and so forth. So the 3 parameters that are crucial for each one of the robots is the camera topic, which is the topic that it is listening to. So it's the topic that gives you the compressed RGB image. The detection topic, which is the topic that it will be publishing the images with the bounding boxes to. And also, which network should I be using? Which set of weights should I be using? And this is, in our example, defined by the network path. Okay, so you can see that robot 1, which uses the elephant images, it will load weights from YOLO V5 elephant experiment number 6, the best one. So these are pre-trained weights. I already trained those weights using just the elephant data set, and I put it here, the best network. So for robot number 2, you see that, okay, it also has different topics for where it's going to receive the images and where it's sending the detection. But it also uses a different set of weights, which is the person weights, the best one after experiment 4. So I loaded it here. And these weights were all trained using regular centralized YOLO 5 training scripts. Okay, so now let's see what happens when we run the detector. So since this is a launch file, we come here. ROS launch. Let me see if I can get the example ROS launch. It is inside my ROS flower package. There we go. Now, YOLO is a little bit heavy in terms of processing. So it does take a while for it to load the detector. And here we are loading two detectors, one for one of the robots and the other one for the other robot. But when you see that detector, this detector loaded, it means that your detector has been loaded. So if we come back to the RQT and we just look at the old topics, we won't see the detection. So what we have to do is refresh so that now we can see the detections channels. For example, here for robot number 1, detections image raw compressed. This is the topic, the detection topic for robot 1. So we click here and we wait a little bit. And yep, this is elephant detected for robot 1. We do the same thing for the second robot. So it will, in this case, it will be robot 2 detection, image raw compressed, and wait. And yep, as expected, robot 1, which train its network only on data containing elephants, it is obviously only able to detect elephants in a scene. And vice versa when we consider the second robot, which only had people data during training. So it can only detect persons. One might argue, okay, this is just like the back of the elephant. You cannot really see it. Well, let's wait and we'll see. So now that we see that these detection work, that individually they're able to detect what they were trained for, but if they're trying to detect both of them, they're not gonna make it. What we can do, let me just stop the detectors now, is going into the federated learning part of this project. So when I was creating this project, I was thinking, okay, what kind of scenario would be kind of useful for people to work on their individual projects. So I don't expect everyone in this session to be, oh, I'm dying to see how I can detect elephants and people using robots.
Pedro,
That's
5 minutes.
What?
5 minutes to end.
Okay. So the idea was, um, let's create a service for ROS service that will behave in a following way. You have the server that will provide you the service of ROS, of training, and you will have multiple clients that will request you this service for training. So the way Flower works is that you have pieces of code that Flowers give to you, like the average, the aggregation methods, and you also have the part that you have to train, that you have to code, like the how do you load the data, how you train your network itself. So when we go into the Flower client, there are just a few methods that you have to implement to create a real federated learning setup. One is here the get parameters. In this get parameters, what is really happening is that the network is telling your server is asking for the weights in your client. When you have set parameters, then the server is sending you weights to your client. The fit method means let me train the network locally, and once it's done, I will send you back the weights. And evaluate is just when you have a validation method for your a validation set to see if your network is performing correctly. Now, I only have 5 minutes, I believe, so I'll skip over some details of the YOLO itself because they're not really relevant. The main thing the takeaway of the YOLO here is that when you're training on YOLO, you have to define what are the classes that you're using. For example, if you're using 2 classes, you have to define that one is elephant and the other one is a person. and you have to define how many classes, like the number of classes. In this demo, we started with two robots doing different things. So the first one only had one class, the second one only had one class. In the federated learning scenario, we have to change the number of classes to 2 for each one of those robots. And we also have to change the tag of the person's of the person's class, not to just 0, which is assumed to be like an integer, a continuing integer counting, but to 1. So elephant will be 0 and people will be 1. And having said that, if we go back to the flower server itself, the way that I envision as it being a service, if you just apply regular ROS coding to it, you will end up having, every time that you connect a client, you will create a new server, and that's not what you want to do. What you want to do is to create one server that will serve all the clients at once. So to do this, I actually had to implement a locking device, for the callback of the service, where just the first client starts really the server. The second client will just wait, and once the parallel training is done, it will get back from the server a link to the weights, the final weights that have been trained, and also some statistics of the training itself. So going through very quickly over the client, since Flower itself, it trains using gRPC, it calls some blocking functions. So the way that you will have to go around this is by creating a separate process for the Flower client, so that you will launch the Flower client and you will continue with your regular ROS node. And this is better explained here in the code. So at this point, since we have very little time, I will just show you what changes you have to do on your data set, mainly for the person data set, so that we can run our final training example. So here you come.
Pedro,
yes?
We need to go straight to the example, because too much information, and then the other speakers are waiting.
Okay, so going directly to the final example, when you guys have time and run through this project, what you end up having to do is to go to the detector and launch the final trained weight. And of course, comment the previous ones. Now, when you Now, if we launch the detector again.
Hey, Pedro, you have an error in your launch file.
Sorry, where?
When you commented, and the first part for the first robot, when you commented, it's not actually commented, because, yeah, that's it.
Okay. Okay, so here, if we go back to our graphic, we see that after updating it, both robots are now able to detect even the partial elephant. So I apologize for taking too long and maybe taking too long with the explanations, initial explanations. I hope the ROSDeck is very well explained so that in your own time you guys can go over this. I really apologize. I hope you guys could get something out of this project, and I'm open to questions.
Thank you very much, Pedro. Thank you. You don't have to apologize, of course. So it's an honor to have you here and that you are teaching us about federated learning and an application, a direct application into ROS. Thank you.
Thank you.
Okay. So then the thing is that we don't have much time. So let's go with the questions already that they are already put on the chat, on the questions tab, actually, of the conference, of the panel of the conference. And then I'm going to go to the most voted one. It looks very interesting. It's kind of, I understand as a kind of hacking the federated learning, right? So the question is from Subhas Das, and he says, isn't there a chance of poisoning the resultant model in some way if some of the distributed devices return bad model data?
That is a great question. And actually, this is a kind of attack that you can do in a federated learning. So this is a great question. Yes. So what you can do is, whilst you're aggregating the weights, you can kind of check on the distribution of those new weights. If they're more or less the same, that means, okay, they're all learning more or less the same thing. The model that I will end up when I aggregate all the weights are good. If, however, I have one set of weight that's completely different, then probably something is wrong. Then either that's an attack or something's wrong with the data. Yeah.
Okay. Okay. So it's so you have to implement in federated learning. You also have to implement anti-hacking systems.
Yeah.
Okay.
Definitely yes.
Antivirus. Okay. So thank you very much. Pedro, we don't have more time for questions, but thank you very much. If you have more questions for Pedro, you can contact him. He has the details on the ROSDeck itself or here in the chat later during the conference. Thanks a lot, Pedro. See you around the universe.
Thank you.